Hello, I am MD Nishat Raihan and my advisor is Dr. Jessica Lin. The title for my CS701 project is Efficient Clustering of Time Series Data. To start with a few definitions and notations, what do we mean by a time series? A time series is an ordered sequence of some real valued data points. As an example here, so the important thing to note here is that this here is one time series, and in the dataset we will have multiple ones like this one. A very good example here can be heart rates database, which is a time series, and the time series subsequence is a chunk of time series that is taken from it, like the one we can see between these two red lines. So our motivation for this project was that in case of most of the time series clustering algorithms, the algorithms have to know the total number of clusters from the very beginning. But we considered a scenario where we actually do not know the ground truth of the number of clusters. So having such a dataset, we try to predict the optimal number of clusters. Like here we have a time series dataset where clearly we can see that there are 3 clusters, but we might not have the ground truth value of this. So our job is to try to predict what will be the optimal number of clusters for these kind of datasets. As for the clustering algorithm, we chose the symbolic pattern forest. As you can see from the critical difference diagram, that out of all the clustering algorithms in time series data mining, the symbolic pattern forest is the best one so far. It's the one closest to 1. So we picked this one for our clustering algorithm. Now how this works is that it actually converts every single time series into a series of words, and then it looks for randomly selected patterns out of those, and it generates multiple trees like this here in this SPF framework. This here is one tree. Now it asks for a pattern like BC. If the time series contains it, then it will go to one cluster. If it doesn't, then it will go to another cluster, and there will be several trees like this one, and all of them generates an ensemble to finally generate the clusters, the final clusters. Okay, but the limitation for symbolic pattern forest is that it actually needs to know the ground truth of the total number of clusters beforehand. So here we want to predict, if we do not know the actual number of clusters, how many clusters should be there. So for our clustering metric, we are using the silhouette coefficient. The equation here is that here S is the silhouette score that we are calculating. B actually means that the average distance from one time series to all of the time series that belongs to different clusters, and A means that average distance from one time series to all the time series that belongs to the same cluster, and then it's divided by the max of those two. The output can be between -1 to 1. 1 means it's very good, -1 means very bad. So actually here we have the results. We used the SPF to predict the output. We generated 2 number of clusters, 3 number of clusters, and up to 10, and we calculated the silhouette coefficient for all of those clusters, and we can see that it was maximized at 4 number of clusters, which was actually the total number of clusters in this case. So when we used the silhouette coefficient on the raw time series, the results are not very good. Most of the cases, like here, if the total number of clusters is 4, it is predicting 2, and most of the cases it gets wrong. Some of the cases it might get close or right, but in most cases they're wrong. And we ran it on 20 datasets, and you can see that in most cases the red ones are wrong. The lime ones are when it predicts 1 more or 1 less than the actual number of clusters, and the green ones are right, and the accuracy here is just 20%. So our approach, the approach we proposed here, is that we normalized the data first, and then we did some dimension reduction. After that, we converted the time series into SAX words. We will go into more detail of what SAX words means, and we use those SAX words into bag of word vectors, converted those SAX words into bag of word vectors, and finally we used those bag of word vectors for the silhouette coefficient to determine the optimal number of clusters. We also used the same SAX words to generate some TF-IDF vectors, and we use those TF-IDF vectors for the silhouette coefficient to determine the optimal number of clusters. So as usual, we did some normalization. We used gnorm for this to do the proper scaling, as you can see here. After that, we did some piecewise aggregate approximation, which actually reduced the dimension of the time series while preserving the actual shape of the time series. As you can see, before the length of the time series was 600, now it's 50, but the shape is all right. Now we convert those time series into SAX words. Now what this means is that SAX is an algorithm which stands for symbolic approximation. SAX is an algorithm that converts the time series into a series of letters. It takes two inputs. So we split the time series into subsequences and convert them into words based on the alphabet size. So it takes two parameters. One is the window size, one is alphabet size. Here the window size is 8. So when the window size is 8, it takes it slides a window of size 8 to the time series, and it converts those windows of length 8 into words that contains where the alphabet size is 3. So when it's 3, it means that the words will contain 3 letters, A, B, or C, like that. So now we have our time series converted into a series of SAX words like these ones. Okay. Now we use those SAX words to finally generate some bag of word vectors. Now what the bag of word vector means that how many number of times each time series contain a single letter, every single letter, okay, every single word, okay. So for this time series 1, this letter doesn't appear any number of times. Also this one didn't appear, but this one appeared once, this one appeared twice, and now this vector represents the bag of word vectors for this time series. Okay, now we have a bag of word vector for every single time series in the dataset. Now we used those vectors to predict the number of clusters, and we use the Shewhart coefficient on those bag of word vectors, and we can see here that our results are quite satisfying here. For the actual number of cluster 4, it peaks at 4. Here for 5, it peaks at 5. For 3, it peaks at 3, and so on. And for the 20 datasets that we used before, the results seems quite good. We can predict the actual number of cluster 55 absolutely correctly for 55% of the time. It gets close by 1 for 30% of the time, and it was wrong only 15% of the time. Now you also generated some TF-IDF vectors now from those same SAX words. Now TF means it actually calculates the frequency of a word in a time series. Okay, so TF is calculated by the occurrence of words in a time series divided by the total number of words in that time series. IDF is actually the measure of importance for a word. Now this is calculated by taking the ln of the total number of time series in a dataset divided by the number of time series containing that same word, containing the word. Okay. Now TF-IDF is simply the product of those two, and this gives more weightage to the word that is rare in the dataset. And now it serves two purposes. It gives more weight to the word that is rare in the dataset, and it provides more importance to the word that is more frequent. Now that we have these vectors, when we use Shewhart coefficient on these TF-IDF vectors, we get results like this. Also, these results are pretty good. Here it peaks at 4 for 4 number of 4 time series. Here it peaks at 3 for actual number of clusters equal to 3. Now for all the datasets, as you can see here, the TF-IDF vectors gives us the correct results for 60% of the time. And here we had to do some parameter tuning. The SAX window size and the SAX alphabet size were not same for all the data series, and we have to find the perfect parameters for every single data series. And also there were some parameter tuning for the minimum frequency of the words and the maximum frequency of words. Like these means that if a word was present in the dataset less than 0.01% of the time, we didn't count those words, and if it was present more than 90% of the time, we didn't use those words. Those are the two parameters for TF-IDF vectors, and these were the two parameters from before. Now if we compare our results with the baseline, our results are pretty good. like from it's a jump from 20% to 55%, 60%. To conclude, we plan to use more datasets from the user archive to certify our claim to from as the improvement on the baseline. We plan to perform further experiments and modifications to improve the accuracy to predicting the optimal number of clusters. Here are the references. Thank you.